Hello viewers, welcome back to our TOC lecture series. In this lecture, we're going to know about regular expression. What is regular expression? What about the basic identities and some few examples? So actually, it starts with the expression that the regular expression is used as a tool to express regular languages or regular state. Regular language, we already know, is recognized by some DFA and NFA. So we can say that there is a connection between finite automata and regular expression. That is, we interchangeably can have NFA or DFA for regular expression, and for regular expression we similarly can have for DFA and NFA representation. So next, let's talk about the formal definition. What is regular expression is any null or lambda, empty string or null string, or any single letter which is part of the input symbol alphabet set, so are trivially known as regular expression. This is called the primitive regular expression. Second, now when you have one regular expression R1 and R2, so in that case the combination of R1 or 2 like OR and concatenation R1 and 2 or R star closure or parenthesized expression R1, all are regular expression. In the string is regular expression if and only if it can be derived from some primitive regular expression like a, lambda, alpha, something like that. So now let's look for examples. In example 1, there are list of few languages consisting of 101 or AB, something like that. For A, we can see all are part of this 0 or 1 part of belongs to input symbol. So these are all regular expression. So 101 is the regular expression for the corresponding regular language. Now B, for B again similarly AB belongs to input symbol, so these are primitive regular expression, so writing it one after another becomes the regular expression. Now for the C, this comma indicates there is a possible different variation of these strings, and 0 are also part of the input symbol, so we use the plus symbol here, and this can be represented by R1 and maybe R2. So R1 plus R2 also regular expression. In this string we have lambda and then AB, so similarly we can write lambda plus AB is a regular expression. For here for this problem there are 4 type of strings, so we write by using a plus sign for the each of the string, and it becomes, so you can say that R1, R2, R3, R4, so all are combined in known as regular expression again. Now this is a full-fledged example of regular language. In this, does any combination of zeros are possible along with the lambda. So we already know in the first few lectures of TOC that this kind of representation is actually represented by star closure. So it has 0 star. For this type of the last scene, we can take one out of these regular languages, and so that becomes lambda, then 1, then 1 1, something like that. So this is 1, and the in closing brackets this becomes a star closure. It can also represented by plus closure, because in the plus closure we know that string without lambda is called a star plus closure. So for the last problem we have two types of representation. Let's come to the second example. In the second example there are three problems. To start with A, here the problem is stated with a concise argument like the state of all strings of zeros and ones ending with 00. So all combination of zeros or 1 represented by 0 plus 1 star closure. Now if it ends, every time it ends with 00, so we concatenate with 00, so it becomes the solution. For the second problem, set of all string zeros are beginning with a 0 and ending with 1. Similarly, the same reasoning, we use 0 plus 1 closure, start with 0, ending with 1. And the last scene, we see there the strings always in even number of 2, power of 2, we can say that. 2, 4, then 6, 8, power of 2. So this is 1 1 closure. So these are the two very simple example. Now let's come to few identities. These identities are very important. These identities are very important because it can be used to reduce any general regular expression or a big regular expression. So the start with a null, phi plus r becomes r. Phi concatenated to r gives phi. Lambda concatenated to lambda, left or right, provide the same result. Lambda closure lambda, but phi closure gives lambda. R plus r always gives r, the same string. R closure is equal to r closure. R closure, this is a just commutative nature. R closure r double closure is same. Now comes the three very important identities. Lambda plus r closure equal to r closure, or equal to lambda plus r closure. PQ whole closure, P is PQ, this is associative. P plus Q whole closure equal to P closure, Q closure, whole closure, equal to P closure plus Q closure, whole closure. Okay. And last come the distributive law, left and right it will both supported. So these are the all exhaustive list of identities in regular expression, and among which 9, 10 and 11, three identities are, these three identities are very important. We will see in the next few section. Okay, now comes the important theorem, which is called Arden theorem. What is the statement is as such that if P and Q, P and Q be two regular expression over sigma, and P does not contain any lambda, then the following equation, that is R plus Q equal to Q plus RP has a unique solution R QP star. So this is the equation and its solution is R QP star. This result is very much important. I'm saying this important because this result can be used to minimize any large size regular expression. So we will see how it is used in reduction of regular expression. Like for example 1, in LHS we have lambda plus 1 star 0 1 1 whole star, then again 1 star, then 0 1 1 star, then whole star. So we have to prove that this LHS equal to RHS. Okay, so start with, say this is R. Let's suppose this is R. So the left side becomes lambda plus R star, which we have seen is in identity 9. So from that we can write R star, that is 1 star bracket this whole star, then whole star. Now again we assume that P equals to 1 and Q equal to 0 0 then star. Okay, sorry, this will not be there, only Q 0 0 1. So in this identity, okay, P star Q star whole star is equal to P plus Q star. So using this identity, okay, R star equal to this star, that means P plus Q whole closure, that means 1 plus 0 0 1 closure, which is RHS. So we have seen that using these simple identities we can get from here to here. Now let's come to the example 2. Example 2. Again we start with LHS. Now we can see that here this is a common part, so we can take out outside. So what is left is first is lambda, then the remaining part of the LHS. So this is again become the case of lambda plus R closure R, which is equal to R closure. If we assume this is this is R, so we have here something like this. So again from here 1 we can take outside 1, and what is left is lambda plus 0 0 star. Again it is lambda plus R star, something like that. So the result become R star 0 star, so 1 is there and the remaining is here. So we get this, which is RHS. So get again this. So in this whole lecture we have seen what is regular expression, how we express regular expression for the regular languages, different kind of regular languages. For example 1, example 2. Then we have seen the different important identities, then the important theorem that's Arden. This result is very important, and using those Arden theorem and outcome, we have reduced some of the big regular mustard size regular expression to some smaller size useful expressions. Thank you so much.